Thursday talk about some stuff with angles of elevation, angles of depression. You guys remember last year you did that stuff with those clinometers? So you had the protractor on the string with the paperclip. You're looking up, looking down. So we do stuff like that. In this class, we take it a step further. I know you guys did some word problems with those before. I make them a little bit more difficult. You're welcome. But again, it's a lot of, can you draw the pictures out and show what it looks like, the difference between elevation versus depression. It's pretty easy when you get going on that. Then probably by Friday, we'll be able to start law of sines. Now, if I'm not mistaken, you guys also did law of sines last year, correct? You know, when you had the non-right triangles, you can solve sides if you had stuff like that. You did law of sines. Did you guys do law of cosines also? Yeah. Okay. So we're going to do law of sines, law of cosines, but one of the things that we add in, with law of sines is we talk about what's called the ambiguous case. I don't know if Seb explained to you guys that sometimes when you have law of sines, it just doesn't work. Or you can make a second triangle out of it. There's a lot of little subtle nuances with a lot of that, and I don't know if we'll get to that part of it this Friday, but we'll definitely get to it next week. Here's crossing my finger. I may or may not have jury duty next week. I'll find out next Sunday night. So if you see me on Monday, I didn't have to go. But if you don't see me on Monday, I'm telling them to fry them for minor traffic violations. And then hopefully, knowing a lot of police officers will get you out of it. Whatever. Anyway, it's kind of where we're at. Okay. No. We do what chapter 12 is. I think is that the probability one? I think that's probability. I think it's a good chance it is. The dad joke, I get it. Well, I'm not exactly sure. What we do here is we're going to do chapters 13 and 14. And with chapter 13, I start with 13.1, and then I skip to 13.5, 13.6. 13.2, 3, and 4 all kind of deal with the same stuff, and that deals with radians, and it's all basically goes to non-calculator stuff. So I like to split trig into two portions, calculator, non-calculator. So the first couple of weeks is all the calculator stuff, and then the next month and a half is non-calculator stuff. And then by the time you get back to your calculator, you'll be like, what is this thing? I get to use this? This is weird. So, but don't freak out. It winds up being pretty simple. I'm going to show you why we don't need calculators in a little bit here when we talk about some special right triangles. So when you guys went back to right triangle trig a long time ago, you know that obviously you had to have a right angle, which gives you a right triangle. When you had right triangles, you had different sides. One of the sides never changed its name. That one was the hypotenuse. In a right triangle, which side length is always, always, always the hypotenuse, no matter what? The longest one, the one that's across from the correct. And what I always dealt with trigonometry is that I always looked at it in terms of perspective. You guys know what I mean by perspective? What does that mean? Yeah, how you look at it. So depending upon how you look at it, the hypotenuse is one thing that never changes. No matter where this is positioned, it will always be across from the right angle, no matter what. But the moment I pick an angle, you guys remember that symbol? Theta. Very good. Theta. Yeah. it's the Greek letter theta. It stands for, a lot of times in the Algebra 2 books, you'll see that for angle measures. And I think you might have seen a little bit of that in geometry. If not, no big deal. So when you have this Greek letter theta, that means you're looking for an angle. Now remember, angles always look at the side that is opposite. Okay? Yes, sir. Yeah, that's the actual symbol of it. That's what theta is. Yeah, that's what the theta looks like. That's something different. But yeah, I know there's one that looks like this. Is some weird. This is what theta is usually like that. Correct. All right. Now remember, angles always look at sides opposite. And if you have an opposite and a hypotenuse, what's left? The adjacent. So I always label my opposite first because I know what I'm looking at. Hypotenuse never changes, so that's the one you always be able to figure out. And adjacent is the one that's by process of elimination what's left. And then that allowed you to then talk about your first three trig functions: cosine, sine, and tangent. When you talk about cosine, sine, and tangent, or sine, cosine, tangent, however you want to look at it, you had the sine of theta, you had a cosine of theta, and a tangent of theta. These were the three trigonometric ratios that you guys learned. Last year we talked about only these three, and basically what it meant was that any angle will always have this ratio of the sides, depending upon their opposites, adjacents, and hypotenuse, of what value you're at. When we said sine was always what over what? Opposite over hypotenuse, good. Cosine was adjacent over hypotenuse. And then last but not least, tangent was, and the really easy thing that we learned about this was this. We talked about it in terms of what was called SOHCAHTOA. And when we use the acronym SOHCAHTOA, that just basically meant sine is the opposite over hypotenuse, cosine is your adjacent over hypotenuse, tangent is your opposite over adjacent. No big deal. I know that all of you guys have done that before, and it hasn't changed. What will change today is that not only do we have sine, cosine, and tangent, we also have three other trig functions that are inverse of these trig functions. When you inverse something, remember, you're basically flipping the fraction. So you get what are called the inverse trig relations, and I'll show you how these are going to work here in a second. The inverse of sine is cosecant. The inverse of cosine is secant. And the inverse of tangent will be cotangent. And when I'm talking about these things being inverses, that just means instead of being opposite over hypotenuse, it's going to be hypotenuse over opposite. And I'll show you what I'm trying to get at with these here in a second. And there's really no fancy moniker for cosecant, secant, cotangent. There's no Koa. Cho, Sha, Keo. Cho, Sha, Cow. Yeah, see, ciao. Ciao, Bella. All right, it's Italian. Mangia. Anyway, here's what I mean by this. When you have right triangles, how many sides do you have? 3 of them. Very good. So if you happen to know, if I place a theta, and I say that the sine of theta is 4/5. That means that the 4 is the what? And 5 is the hypotenuse. Good. That means that I have an opposite of 4 and a hypotenuse of 5. Because that's what the trig ratios stand for. Now, if I ask you what the secant of theta would be, that means I have to find that missing side length and build out of it. Now, do you guys remember special patterns that were within some of these? Remember, there are these things called triples. They still show up pretty regularly. If not, what could you always fall back on? Pythagorean theorem. Anytime you have 2 out of 3 sides of a triangle, if you forget triples, if they're not 1, you can always fall back on that. But if you recognize and you remember there's certain patterns, 3, 4, 5, 5, 12, 13, 7, 24, 25, 9, 40, 41, 8, 15, 17. I think that's all we did. Usually it's 3, 4, 5 you see more than anything. So I know that my adjacent in this case would be 3. Secant hypotenuse over adjacent, so it would be 5/3. We'll start to see more of that as we go along. Just a little new bit right there. Okay. Not bad. You all right? Yeah. Yeah. That's fantastic. It's really, I don't know who drew that. That's very funny. You're probably right. Now when you start thinking about solving for missing side lengths, this is where some of the things that I teach in geometry help out a lot in this class, especially for right triangles, because a lot of times you guys will have a tendency to go way too fast with the problem. And what I would always suggest that you do is these following steps. If you're trying to find a side, or if you're trying to find an angle, or in a minute here I'll talk about what's called solve the triangle. What you always want to do is start with what you know, and always reuse what you're doing. Okay? In this example here, I'm trying to find that value of x. I know what the angle is at 37, and I know I have a hypotenuse of 12. I've always taught it this way, as you go to solve these things out, is always circle the angle that you're working with. Draw a picture to your opposite. Or sorry, not a picture, an arrow. So what you're looking at, you're always looking at the angle opposite you. Immediately label the hypotenuse, and then by process of elimination, what's left? Adjacent. What trig function uses adjacents and hypotenuse? Cosine. So we would use cosine in this case. Cosine of 37 is our adjacent over 12. Little known fact, I don't know if you guys remember this, is that sometimes, I can't remember the whiteboard, Devin won't see it. If you're trying to solve for side lengths, your algebra is only going to look like one of these two. If you know an angle and you're trying to find a side, your unknown is either going to be in a numerator or it's going to be in the denominator. What I mean by this trig of theta means it could be sine, cosine, tangent of any of those numbers. That number symbol, I guess you guys call it hashtag. I don't even know what that is. But it's the pound sign. I don't know if you've known that. It's the number button. It used to be on the bottom right-hand corner of what's called a payphone. I saw a payphone this weekend. We went to the auto show and there was a payphone. No, my kids picked it up. We took a picture of it. It was pretty funny. One of them had the cord where it was upside down. Hello? Did they know that? So, nice little shortcut here. Whenever you're trying to solve for the numerator, all you do is multiply across. You just move the denominator. Because if you think about it, it's x divided by 4. How do you undo divide? Multiply. So you would write 4 trig of some angle. Right? If the unknown is in the denominator. Remember how we've talked about this pretty regularly. Fraction equal fraction, what do you do on the diagonals? You exchange-o, change-o. So if your unknown is in the denominator, you just swap out and divide by the trig. Remember, that trig stands for anything. Okay, it stands for sine, cosine, tangent. I just wanted to show you that quick reminder. You'll see this a lot. I know you probably remember it, but I always show this. That way people go, you guys slow down because you go too fast. Plus, if you write down what you're about to do before you do it, I'll know what you did if you did something wrong, if that makes sense. Because in our solving for this problem, you guys all agree we'd have to multiply by 12? Yeah. 12 cosine 37 is x. I am a huge supporter of the idea of always writing down what you're going to put in the calculator before you do it. There are going to be so many buttons you're going to have to press. You got to make sure that you press them in the right sequence. Hit a 3, not a 2, something silly. So if you have this written down and then you give me some answer that's wrong, I can probably figure out what you did. Versus if you don't write anything down, I won't have any idea what you did wrong. Right? Does that make sense? This tells me you know how to do trig. If you get the wrong answer, it just means your thumbs weren't smart. You can't blame your thumbs. Right? Now, one of the things on your calculators I do need you guys to check. This is one thing that's new with these calculators. On your calculator, there's a button that says mode. Hmm? The button that says mode, you'll see that there's like the third or fourth one down says radian and degree. Whenever we're using calculators for trig, you always have to be in degree mode. I don't know if yours have been defaulted back and forth. All you have to do is just press the arrow button on it. Hit enter and it highlights it. Okay. Now, whenever you're using your calculator and you haven't used it for a while, you charge it, you have to reset it, if you have to do the memory sweeps or whatever, anything like that, you have to go back and press the mode button to put it back into degrees. These calculators default to what are called radians. Okay? We haven't talked about those yet. Those are something new. I'll explain that here in a little while. But for all of our buttons, whenever we're pressing an actual button to say sine of 13, it has to be in degree mode. Okay? You all right with that? I don't think any of you guys have one with batteries. Like we all have the chargeable ones, right? Yeah, okay. Because some of the older style ones, if you have any friends in the regular algebra class, we still have a bunch of the older ones. If anytime the batteries fall out, it resets everything, so you have to go back and reset it to degree mode. So just one of those. So back to this one, all you have to do is literally type it the way you see it. Hit quit, and you type in 12 cosine 37 and hit enter. I'm going to ask that you always round to 2 decimal places. And if I round to it was 37, wasn't it? Yeah. Okay. For some reason, I wasn't sure if it was 37 or 39 because I'm old. When I do, you could have said, no, you're not. These jerks. Anyway, so when I go to this one, if I'm going to write it out in terms of 2 decimal places, I always look at the third. And if it's a 5 or greater, I round up. If it's not, I just keep it the same. This one is 9583, so my answer would be 9.58. And I go on my merry way. The reason that it does that is because of this. Do you agree that if I say this is 0, 90, 180, 270, 360? You okay with that? Okay. Now, if I go all the way around, I make a circle, don't I? Albeit it's poorly drawn. Now, when you're talking about the circumference of a circle, that's what? 2 pi r? 2 pi r, r stands for the radius. So if I put my radius at 1, what's the circumference of this circle? 2 pi. The radius would be, the circumference is 2 pi. It takes you 2 pi to get around a circle. So if I start at 0, if I go halfway, well, what's half of 2 pi? 1 pi. What's half of a pi? Pi over 2. And then down here would be 3 pi over 2. That's how these things break into radians. Radian measures deal with it in terms of pi. Now, what's halfway between pi over 2 and 0? Pi over 4. What degree measure is that? 45. So this is pi over 4, which happens to be 45 degrees. Okay. What's a third of 90? 30. What's a third of a half? Here's 30. Here's pi over 6. Isn't 60 degrees double 30 degrees? So wouldn't that be, instead of pi over 6, it'd be 2 pi over 6, but we write that as pi over 3. And that's how radians work. And It's in terms of degrees versus in terms of pi. We will need to know how to do all that, and it is really, really easy to do. Because this value here replicates itself here, 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 and here as you go around the circle. One of the things you'll notice, these are just going to be ordered pairs. When you talk about ordered pairs, it's just some x and a y coordinate. You guys agree with me on that? When you're talking about verbal, when you're talking about x and y in terms of the quadrants, what's positive and what's negative in the first quadrant? They're both positive. What's positive and negative in the second quadrant? Negative, negative, positive. Watch this. If you take your calculator and you type in the cosine of 30 degrees, you get, what would that be? Point something or another? 866. Okay, multiply that by 3. Square it. Wait, I did something wrong in my head. Oh, it's times 2. I'm sorry, times 2. So cosine of 30, I'm sorry. That's right, so it should be 3. Sorry, I did the backwards. It's supposed to be times 2, then square it, not times 3. So you get what basically winds up being root 3 over 2. Who has a multi-view calculator on them right now? Take your multi-view calculator out real quick and type in cosine of 30. It'll spit out root 3 over 2. Now, if I'm over here at 180 degrees and I go up 30 degrees from it, that means I'm 30 degrees less than 180. That would be how much? 150. What's the cosine of 150? Type in your calculator. You get negative root 3 over 2. If I go 30 degrees past 180 degrees, it means I'm adding to it. That'd be 210, wouldn't it? What's the cosine of 210? If I do 30 degrees less than 360, what would that be? 330, which would be, because those reflect into the different axes. Hey, it is, and that's where all of this is geared towards. Okay, we use these special right triangles to be able to build this stuff out. I was going to show this right away, but it worked out perfectly. You asked about that question. So we'll get to all of this eventually. But the reason that all of this trigs, if you will, is because you guys learned these two triangles. Yep. You guys learned about the two what we call special right triangles. And when we dealt with the special right triangles, we had special ratios for the side lengths. And if I'm not mistaken, Seb used Q's, didn't he? Yes. He said Q, Q, and Q root 2. Okay. Just for fun, because it's always awesome. That's my opposite. That's my hypotenuse. What's the sine of 45? Sine of 45, according to my diagram here, would be Q over Q root 2, wouldn't it? One over root 2. And do we like radicals in the bottom? No. It's root 2 over 2. Okay. Just, that's why all of this works, because those Q's that you used last year will simplify themselves out. Do you guys remember the trick, or did you ever show you the trick when you're solving for missing side lengths with specials? If you had, if you were given a whole number across from the 90, let's say that this part equaled 8. And I want to figure out what the other two parts are going to be. I don't know, 2 root 2. I think you're hold on a second here. I think you're ahead of yourself here. What I have always done, I never used Q's. My Q's look awful. I use X's. Now, when we talk about trig, I always talk about it in terms of what is it looking at? It's looking at a side opposite it that was X, X, and then X root. I'm just going to switch to X's because I can't draw a nice clean Q. You okay with that? I can do a Q if you want. In this case, we knew that across from the 90 was equal to 8. How do you solve for X? Okay. That's a joke. How do you undo multiplying by the square root of 2? Divide by the square root of 2. And then how do you rationalize? What's the square root of junk times the square root of junk? Junk. So you get 8 root 2 over 2, which is 4 root 2. Remember what the shortcut was? Cut it in half and slap a root 2 next to it. Yep. Works every time. Doesn't matter what it is. If you have a 45, 45, 90, and you are given across from the 90 to solve for the other sides, all you have to do is cut it in half and slap a root 2 next to it. It'll work every time. Every single time. If you have a 45, 45, 90, and this is 12, these will be 6 root 2s. If you have a 45, 45, 90, and this is 11, there's no such thing as decimals. 11, cut it in half, you get 11 over 2, and slap root 2 next to it. Like you said, 11 root 2 over 2. That was the shortcut. Works the same way with 30/60s, but very subtly different. Instead of dividing by 2, you're going to divide by, there you are. 30, 60, 90. You have ratios of x, x root 3, and 2x. Eventually, you're going to say it's just 1 root 3 and 2. It works the same way. If you're given across from the 60, bless you, if this was equal to 9, you'd have to divide by the root 3 and rationalize, which meant you would be just dividing by 3 and slapping a root 3 next to it. That would equal the value of x. And if I double 3 root 3, I'm going to get 6 root 3. You'll see some quick pattern stuff here. There's not a ton of it. There really isn't in Algebra 2. It's more of reminding you of why those ratios work, because we're going to use them more when we get to the unit circle in about a couple of weeks. Okay? But for now, it's just a quick remembrance of the ratios of the sides being x, x root 3, and 2x, and just setting them up through there. There's really not even that many problems in this textbook with them in there. Excuse me. Other than that, we have to also look at one other style problem real quick. I think, before I get too far ahead of myself here, is what does it mean to solve a right triangle? Do you guys remember that? Yep, all the angles and all the sides. Now, sometimes it'll say triangle ABC is a right triangle. If it's the middle letter, that's usually what they deem being the right angle. Sometimes they'll give you a diagram and say, hey, here's angle A, here's side A, here's angle B, here's side B, whatever. When you're solving a triangle out, all you need is one side and one angle, or you need two angles, or two sides and no angles, because you can work your way through everything. What I would do is I would always draw my picture and label what I'm looking for. And as you do that, it's just kind of, this first couple of days of trig stuff is really big time procedural. Follow the same process, follow the same process, follow the same process, and go on and on and on, and go from there. So in this one here, if I fill in my blanks, angle A is at 20, little a is at 12. Remember, big letters are always angles, little letters are always the sides opposite. Do you guys remember that? So when I start solving stuff out, I circle my angle, I draw my opposite, label my hypotenuse. Process of elimination. Everybody all right with that? What trig function am I going to use to find the hypotenuse if I know what my opposite is? Sine. What trig function am I going to use to find my adjacent if I know my opposite? Tangent. What I want to do here is always reuse the given information for myself, so that way I don't make a dumb mistake with something else. We're doing kind of the same thing right now in geometry. We're introducing how do you press buttons the right way in the calculator to solve triangles. And so far today, most people have messed up. And they've accidentally said that angle B, in this case, was 80. Yeah, and a lot of people do, they want to go to 100, but remember, it's got to equal, these two have to add up to equal 90. So if I wrote down 80 for angle B and I used that as a trig function to find something else, I would never be right, would I? No. But even if I still wrote down angle B was 80 like a knucklehead, and I used 20 with the trig functions, I could still get the correct side lengths. That's why I always want to reuse whatever information they give me to start. So like you guys said, I have the sine of 20 is going to be my opposite over the hypotenuse. The tangent of 20 is going to be my opposite over my adjacent. And then I just write out how I'm going to solve it before I press my buttons. My unknown for both of these guys in the denominator, so I just do a quick little change-o. And really, if you're typing it in the calculator, you can use the fraction bar. Or if you want to use divide by, just make sure you don't have anything after the parenthesis of the 20, so you're not adding any other parts to it. It's just being careful on how you type it. Let's see, 12 sine. Oops. Then 12 tangent. Oh, so I did times. I'm doing divide. Sorry. $35.09.
Yeah.
Oh, dang it! All right. And then this one will be 32.97. Not terrible. It's just quick little reminders of how things set themselves through. Do you remember the buttons that you have to press when you have to find an angle? The -1, you know what that stands for? The inverse. You find the inverse. The inverse is how you undo a trig function. How do you undo sine? You inverse sine to both sides. How do you undo tangent? You inverse tangent to both sides. For example, just to make sure we have the button sequence correct, I just want to make sure we set this up the right way. It's not tough, but it's just one of those things that you can accidentally hit sine 12/35 versus the inverse, and get all sorts of messed up. I think I just gave away what trig function it was. Sorry. What's that? I wouldn't either. So circle the angle you're looking for. Draw to your opposite, label your hypotenuse, and lo and behold, you are using sine. And then when you write this out before you type it in, just remember you're using that inverse function from last year. Theta will equal the inverse sine of 12 over 35. And you would type that in your calculator exactly like that. When you type that through, remember to get the inverse button, you know what you have to press first? Second. Yep. You hit second sign, and then it goes from there. The functionality of the calculator for using trig hasn't changed from the multi-view. The only difference with this one is that for the special right triangles, it won't do that. You know, it's root 3 over 2. It won't do that stuff for you. But by the time we start doing trig functions of special right triangles, you won't need a calculator anyway. You'll just be rotating off the ratios of sides. It's a lot easier that way. Does that vaguely ring a bell? Yeah, just funny thing. What did you guys get for that one? 20. Yeah, because what this inverse function is, what's anything with a negative 1 power? It's 1 over it, isn't it? This is 1 over the sine of theta. So if you multiply that times sine of theta, you're left with 1. So you're multiplying by its reciprocal. So instead of dividing by 2, you're multiplying by half. Same basic idea. That's how you're able to undo the sine functions that way. There's another trick here I'm going to show you. This is a lot of info in like 30 minutes. It's a lot of review. It's a lot of info here. Let's get even further. Yeah, just do one more. I won't get to depression or elevation today. We'll do this last one, then I'll give you some problems. I think I already posted it, didn't I? Yeah, solve the whole triangles. Let's see. 1542. Do you guys ever remember whenever you used an angle that was, well, half of 30, if you used the multi-view, did you guys ever remember seeing that it came up like really weird, like root 3 plus root 2 and did all this weird stuff? Do you ever remember seeing that? Okay, never mind. It's a pre-calc thing. 15 is half of what? 30. So as we go along and you get into pre-calc, there's these things we may or may not have time to talk about this. I haven't had time to do this problem yet. There's things called half angles and double angles. Half angle, there's a theorem that follows the pattern of special right triangles being half of 30, and there's ratios and all other stuff we can do. We're not going to get there. And then just type some buttons and go, correct? All right with that? What's angle A have to equal then? There you go. Quick and painless, isn't it? Hopefully that should give you a pretty decent start as far as the stuff goes. Let me pull up the, what do you call it? Prompts real quick.